So, welcome to this webinar where the goal is to talk about how AFP systems will be used as filament winding and why would we want to do that. Before we begin, just want to briefly introduce who is presenting, what is Addcomposites. Addcomposites is a provider of automated fiber placement system, which are compact, plug and play, goes on to a robot. We are based in Helsinki, Finland. We have about close to 30 AFP systems across the world. And now we also have some printer products and more production level systems. In this call, I think with me, my colleague Dave and James are also here. So, in case you have any questions, if you put it in the chat, they will relay it to me for the to pause and take a break for answering that. So that was a brief introduction about Addcomposites. Myself, my name is Pravin. I'm a CEO at Addcomposites, but my major role is mostly running different composites projects within the Addcomposites. So anything that is getting developed new from the application point of view, I'm mostly involved. I have a background in space industry, mostly related to launch vehicles and satellite structures. And now with the building of the company, the AFP systems and how to automate the production with composites. With that, I will start. So we will have mainly three parts in this presentation. We will start with the very basics of filament winding. We'll start to ramp it up, AFP, FPXS, and then trying to define what is this AFP filament winding. Then we'll dive later into why we would want to do it, and then the live demo of the machine running, and then how you can start doing it. So I'm going to have a live programming demo and followed that with the live machine running demo, then the Q&A. Filament winding is I would say, the most used automated manufacturing process for making composites part. It's nothing new where there is a roll or multiple rolls of fiber that are in dry form are stored onto the krills, which are tensioned and then are relayed through many guide rollers and guided towards either through a wet bath or directly dry winded onto a rotating mandrel. And these mandrels could be mostly circular in nature, but need not be most of the time. They can be also wound. In this process, the major limitations seem to be the friction, that the friction angle. So if you wind at, let's say, pole to pole, you won't be able to, because there will be slippage. So you want to always go geodesic, respecting the friction coefficient of the fiber. Thus, you have some limitation to what minimum angles you can wind, also maximum angle. So you cannot do 90-degree, that is like perpendicular to the rotary axis, but you can do hoop, which is like a helical winding. And this has been around since 1960s and even before. Before the name was coined even, and it is the process that is highly available. With that understanding in mind, um, when the industry started to pick it up and they wanted to use the similar set of automation for their fuselages or wing structures, they delve into like, okay, how can we start doing similar automation? So they first started with just laying down wider sheets of UD prepregs, which is what was came to known as automated tape laying machines. And these machines were definitely automated, but they were only limited to very simpler, flatter geometries, because otherwise, as the curvature would get added, they would have the issue with following this curvature, because the long unidirectional prepreg sheets won't drape onto the complex surfaces. Thus, the concept of automated fiber placement came into place, where they started to slit this wide unidirectional prepreg sheet into narrow tapes and put them down into let's say quarter inch, half inch widths, and then multiple of those tapes could be laid down at the same time. Thus, you're able to kind of automate for complex geometries, uh, complexer from the ATL point of view, geometries, which, if you see, it's a kind of an analog to what the filament winding looks like. With an addition to here, we have cut and clamp ability. And in addition to that, the heat got added, I think, around 1990s to increase the tackiness in this type of AFP systems. So 1980s, 1990s saw the rise of these machines, and because this was majorly funded from defense contracts for military purposes to begin with, and then later on aerospace, the systems were heavily expensive. So I would say before 2000s, you can say there was like 10 AFP systems, maybe at max. So that's like the AFP, and that's kind of also like where we are now in the similar trend of AFPs. Now the AFP systems that you find, like the one that we provide, which is very compact and can be mounted onto existing robots. So also the number of robots have exploded. Let's say since 2000, almost for every one person you can find a robot, industrial robot out there. And because of such high number of these robots, basically, if there is this such compact AFP that is not only able to do thermoset but thermoplastic and dry fiber placement, it greatly enhanced the total number of AFP systems. I think I would say it's now still not very high number, but in range of hundreds somewhere at the moment, the total number of AFP systems in the world. The benefits now with the advancement of software and robots available, that these systems are able to do all the complex geometrical shapes and as well as do the selective reinforcement, and are way more precise than those, I would say, few million euro systems. And these are now very similar, costing very similar to a winding system. So this is basically the journey up to AFP, and then there's a winding system. Given the background, why do we need to do winding with the AFP? So having to now seeing the huge trend in moving towards thermoplastic, seeing the capability that AFP has now developed, the capability to do continue be able to place thermoplastic. The first process that came to being is the tape winding, which is where you have the compaction roller touching the mandrel, is rotating continuously, and the heat input is there at the same time. Thus, you're able to do thermoplastic winding on the mandrels. What this enables is now filament winding, which is limited to either dry or wet winding or prepregs. With tape winding, you're able to do thermoplastic wounded shapes, which is is where we would want composites industry to go because of the sustainable and recyclable nature of the thermoplastic composites. Given we have, once again, now the AFP that is able to do up to this extent, the need to have a filament winding system start to come into a question. Why do we need a filament winding system where tape winding systems are already quite capable of doing the circular geometries? Answer is, if you keep constantly have to be in contact while doing the winding, there are regions you reach where you will collide with the shaft of the mandrel, and because you are always in contact, you have to follow the geometry, which in case of filament winding you don't have to. And that is why the need for having the filament winding with AFP come to be, where you can eliminate to have a winder altogether, and you can just use the existing AFP as a filament winder, where the your AFP, which is already so much more capable, as just one feature through programming, and then now it's able to make everything that a filament winder can make, plus everything that an AFP can make. There are some caveats, we'll talk about them, but that is what the AFP filament winding is. As you can see in the image, the tool is hovering far away from the mandrel, yet winding almost the perfect shape as a filament winder would. So this is the basics of like what and why of the filament winding with AFP. The next bit is to more focus on, like, now once we have combined these abilities, what it brings out. I think I would like to show a demo, a very brief demo to showcase if I would do tape winding, what would happen for a tank. So here I have a simple tank that is set up to tank at some angle degree rotation. And I have here through AdPath, I've already planned this tank. As we would see here, what would happen, the robot would collide and is already reaching its motion limits. Yeah, I think we can kind of see the awkward position the robot has to go to. Thus, the tape winding is the huge limitation. So this is more visualized compared to what we saw earlier in the slides. Then we go into the applications here. Now, once we are able to do the filament winding, the other benefit that it adds is now you still have the AFP system that's just there. You're able to still do the selective reinforcement in the regions that you, based on the calculation of the design, suggest that there are high stresses going to be occurring in certain region, thus help reduce and the weight further and optimize the design even further. The freedom is way higher to be able to do non-geodesic path in the cylindrical section and also non-cylindrical section. So you can do fiber steering on top of the either existing wounded parts or just to start with on the liner. Yeah, and thermoplastic winding. Now, as we are able to do thermoplastic winding, there is a possibility to still be able to keep the ability to do thermoset dry windings and then have thermoplastic winding as well. And depending on as you see the transition from thermoset to thermoplastic, you're never left out to what your system is capable of. It's only depending on the market demand, you're able to adjust and offer the capability that is needed in the market. Some of the very good examples, which at the moment are limited in filament winding that are not possible, but AFP is able to offer, is you are able to first do the winding, and then whenever you have convex geometry, which with winding, because it is done under tension, is not possible, you're able to go in the convex shapes and use the AFP capability to do the placement. I hear one of the applications, which is a load bearing bracket, where you're doing the fiber steering. Once again, this is more of a hypothetical example because fiber steering at that level maybe a bit too optimistic. But the bracket design with the grooves is actually possible. This is, I think, one of the very famous structures, isogrid structures used in space industry quite a lot for upper stages, but making entry into also automotive. And this, at the moment, filament winding is not capable of doing because the grid is made in such a manner. And then there is the vice versa benefit. So with filament winding, you're able to do hollow winding where there is no mandrel or physical mold, and then you utilize AFP on top of it. So overall, you're able to reach, the combination is, it's only limited by your imagination, like what structure the needs are for the manufacturing of the structure, and then you're able to come up with a solution that basically brings the best out of the both processes. This is one of the very new applications that I feel ready for AFP filament winding. That is the electric motor sleeves, where you're able to do thermoset or thermoplastic, both options. And you're able to use the high tension controllability from the AFP and its capability to be able to do both materials. So you're not limited to thermoset or dry winding. And there is a possibility because the circular nature of the geometry, you're able to achieve, I would say, on top of a existing to wind and in situ consolidate the sleeve. So there is no secondary process. So with thermoset, there's always a curing step, and with this capability, there's only a single step process that you're able to optimize quite a lot. I would say, I think at this point, these are the applications that I've been thinking about in regards to AFP winding. But yeah, let's start with the live demo as we planned. So if you would have to get into doing the filament winding, how would you get started? So first, we'll start with just seeing how the planning would go. So this is just a saved file, but I'll start ground up. So AdPath is the planning software for AFP and 3D printing and filament winding, as you can see. And here I can show the type of geometry that I have inputted. So this is a step file geometry that I was able to just import from my favorite CAD software. So I use like Autodesk Fusion. So I just created this mold geometry there and just imported it. And I set up the origin of this mandrel at this point. So I selecting the origin point, start of the X point, end of the X point, start of the Y axis, and end of the Y axis. And I know physically my mold is placed at about 140 millimeter away from the flange in the robot, and that is the number that I have inputted, and I have connected it to the external axis one, that is this axis. I started by setting up just the mold. Then let's get into the planning stage. So I can clear here. So let's start with selecting the cylindrical area as it is asking us to do. Then the dome areas. So we can select the dome areas. Then we have to select the directions. So I define usually the zero direction is pole to pole. And then the 90 direction is from is perpendicular. So my 090 is defined at the pole origin. Then I dive into the winding tab. Sorry, just I think I missed. I selected from here continuous winding for cylindrical tank with dome. So once that option is selected, I get this option for adding the cylindrical parameter, that is the diameter of the dome. So I'm gonna go measure the diameter of the dome, the length of this dome, that is from this center point here to this center point here. Same for the diameter of the middle section that is sketched out here, and then the length of this cylindrical section. So this center point to this center point, and then the diameter of the right dome, that is here, and then the length of this dome section, that is from here to here. So now I have defined where my mold is positioned. I have defined the cylindrical geometry as per this sketch that is given in the stock here. I have no starting offset. I think here I can just plan for some circuits. And when I want to do full coverage, I just type 0 circuits and it plans the full coverage. I have a winding direction based on the setting that we have. And I have the filament winding mode on, where I want my tool to hover about 350 millimeters away from the center axis of the mandrel. With these settings, I go and I start to define the angle. So here, just to showcase, I have 65 degrees angle. and I am using quarter-inch tape. Let's hit plan all. So this should take less than 60 seconds to figure out. And on top, we can follow the progress. So the defined winding angle was 65, and in the dome sections, it's able to not maintain that angle particularly as it start to converge. So it is trying to get as close, but it's able to get to a bound of 43-degree angle. And now it's generating the frames for each of these circuits. So second circuit, I think at the moment we are working on optimizing the process flow. We expect this to become much faster in this planning step particularly, so we are able to run through multiple iterations of the software. As I can see now, the tapes are rendered here. So let me close this down. Let me hide the mold CAD geometry and use the add path generated CAD geometry for better visualization. I can see it has generated the 4 circuits that I have asked for. And let's see the simulation. So as I go frame by frame, we can see the tape it is drawing. So this is where the starting point of the tape is. It's a bit difficult to see, but it's almost at the, if I go top view, it's almost at the middle of the starting of the dome section. And as I start to play slightly higher speed, it is first now putting down the first tape. And as you can see, this is how the process should look like once it start to wind. And in this case, as we can see, it's just working like a normal filament winder, which would wind a tank. Uh, this is, to my knowledge, only AFP system that's able to do filament winding at this level. So we can see and continue to see the program here. Usually with this simulation, what we are trying to notice is the robot within range and it's not hitting or colliding anywhere. And we are happy the way the layout looks like. If this number of circuits look right, you would plan for the entire geometry and add more layers as you would like. AddPath would automatically plan the transitions between the layers and would generate the program after that. Here's a program tab, and you would come here, you just select a winding post processor, and it would generate depending on the selected robot. So in this case, we have a KUKA robot. But if this was a ABB, Fanuc, or a Kawasaki robot, it would generate the code for those robots' understanding. Yeah, so I think this was mostly in how you would plan for a filament winding using AFP AdPath software. So I think we did a live demo on the side of the software. I think now we should go to the live demo of the system. So I'll hand it over to James.
Hopefully everyone can see my screen. So like Pravin said, we have the AdPath filament winding circuits planned. So we just transferred that program over to the robot. So now I'll just play the actual program so that we can see the physical tank that we just planned.
Awesome. This is just at the moment, I think James is running it slowly because he's just starting the program. But this process, once you have set the system right, you can run it at highest speed that the robot would offer. We can see already the pattern here. So this one is number pattern 5. So you'll see a 5-star come at the edge. So it's at the moment drawing in a way that it is, yeah, it will do 5 circuits before it start to put the next tape very close to it. Yeah. In this case, I think I can give a bit of a background of what systems we are using. So this is a PA12 polyamide tank. that is mounted onto the positioner of KUKA, and it's winding the pre-preg tapes from it's toe pregs from one of the suppliers from France. And the system uses no heat as such, as you can see, and it can run pretty much autonomously in this case. I think in one of the screen that James has there, yeah, it's able to run with the pan spool and also with the bobbin material storage of these systems. With this, I think James, if you can pause it, we can take up some questions if there are any, and then try to go through if there is anything that we have to show in this regard. Yeah. But yeah, I think in typical webinar fashion, we still have some time here to talk about the system, but it's not necessary to ask all the questions like in open. So you can definitely contact us directly. In the call with me, my colleague James and Dave both are here. So in case you have any questions regarding the filament winding capability with our single toe, multi toe, or filament winding system, yeah, they would be able to answer. Yeah. And with all of these systems, the capabilities are widely available. So usually, just going into the process for the structural winding, planning such winding starts with the structural requirements that your FEA provide. With Addcomposites, we work with Altair. So if you plan anything, you can import the FEA mesh from Altair and get the actual fiber placement position into the mesh and know exactly how the thickness buildup would affect the structure that you have planned for. Thus, the interoperability with such very, I think, industry leading FEA software really helps you kind of have very simple workflow build up. And we'll share the slides with all the attendees, so then, if they have any doubts on any of the demo pieces showed here, please feel free to reach out. We really appreciate everyone joining in on the call, and we hope to continue doing these style of webinars almost every month. They would be focused on mostly new products and applications. So the same topic won't be repeated. I really appreciate you visiting us on the website, and usually the sign up forms are up to date on these upcoming webinars. So please sign up. And I think from at Composites team side, really thank you for joining us. Thank you.